In this video, I'm going to analyze a ball being swung in a vertical circle, as you can see in the picture. And we're going to look at that ball at three different locations, A, B, and C. So the top, the middle, like the 3 o'clock position, and the bottom of the circle. And we're going to draw a free body diagram at each of those locations. So here, this will be the free body diagram for point A. And so when it's at A, the string is pulling down on it, and the string pulling down on it is a tension force, and then the weight also acts down. Those are the only two forces. There's one contact force and one non-contact force. Next thing to finish off this free body diagram would be to draw in the coordinate system. So since the ball is moving in a curved path, we want to have an R direction, which is going to be this way. And then if we say that the ball is moving counterclockwise, then this would be the positive T direction. Okay, and that's a lowercase t for tangential, and this is a capital T for tension. So two completely different meanings for T there. And then of course we also have lowercase t that we use for time, but time doesn't come into any of the equations here in this unit. So now we'll look at figuring out how big that tension is, so we can sum the forces in the R direction, and that's equal to ma sub c, and tension and weight are both in the positive R direction. We always do the positive R direction in towards the center of the circle. And we're trying to find the tension, so it's equal to ma sub c minus w. A sub c is equal to v squared over r. So even if the ball is going around at a constant speed, it's still accelerating because it's changing direction. And so A sub c is equal to 4 meters per second quantity squared, different than 4 meters per second squared. That would be an acceleration, divided by 0.6 meters. So A sub c is equal to 26.7 meters per second squared. And we can fill this in. Tension equals 0.100 kilograms. I converted from grams to kilograms, times 26.7 meters per second squared minus 0.1 kilograms times 9.8 meters per second squared. And the tension is equal to 2.67 newtons. We see kilograms times meter per second squared. That gives units of newtons, and the same thing here. And so that is our tension at the top of the circle. All right, and now we can look at point B. Okay, so over here. So at point B, well, the weight is still acting straight downward, but the tension now is acting to the left. All right, and we need a coordinate system. Now we had a coordinate system before, but you have to recognize that it's going to change. The t direction, I'm sorry, the left direction, the direction that the tension is acting, is the R direction. That's in towards the center of the circle. We see the center of the circle there. So from B to the left is the R direction. And if it's headed in the counterclockwise direction, that means at the moment it gets to here, it's headed up. And so that means this is the tangential direction. And so similarly as before, we're going to sum the forces in the R direction. And so remember, radial is in towards the center, centripetal in towards the center. And so it's going to be T, and that's it. T is in the positive R direction. There's nothing here in the negative R direction. Weight's in the negative T direction, so that doesn't matter. So that equals MAC. So tension equals 0.1 kilograms times 26.7 meters per second squared. the magnitude of the acceleration is constant. The direction of the acceleration is always in towards the center of the circle. So the magnitude of the acceleration changes, but the direction of the acceleration changes, but its magnitude is always the same. And oh, and I just realized I wrote down the wrong value. This value here is incorrect. So let's see. Let me see if I can erase that. There we go. All right, so this was supposed to be 1.69 newtons. I had all the right values there, but I put in the wrong final answer. And so now on this one, at point B, that one does come out to be 2.67 newtons. There we go. And then when we're at point C, we look and so when we're down here, the rope is pulling upward. The weight is downward. Those are the only two forces. And we have to think about which way is the R direction. Well, from C, looking, the R direction, the center of the circle is upward. And it's going to the right at that moment. So that's the positive tangential direction. And then we can sum the forces in the R direction. This is applying Newton's second law. This is what we do all throughout this unit. Chapters 4, 5, and 6. Friction, inclines, connected objects, objects going in circles. They're just various cases of Newton's second law, drawing free body diagrams, picking a coordinate system. So the tension is in the positive R direction. Weight is in the negative R direction. Contrast that with earlier at point A. And then that's equal to MA sub C. So tension equals MAC plus W. So tension equals 0.1 kilograms times 26.7 meters per second squared plus 0.1 kilograms times 9.8 meters per second squared. Remember, W is equal to mg, and g is a scalar, so it's 9.8. It's not negative 9.8. The acceleration of an object in free fall is downward, which often that'll be our negative direction. But g itself is a scalar. We have accounted for the direction already. We accounted for the direction right here with this minus sign. And so if we put a minus sign there, we are canceling out that. And that doesn't work that way. The same thing over here for A. We accounted for the direction right here with a plus sign because the weight is going in the positive R direction. This one comes out to be 3.65 newtons. All right, so I will also point out that if we look at a stationary this is for when it's moving, but if we look at it when it's stationary, and let's see, let's erase that. Let's go with purple. All right, now we say it's stationary at C. Well, we'd have tension and we'd have weight. But if it's stationary, we won't have a positive R direction. Instead, up will be our positive Y direction. And so then we can sum the forces in the y direction, and it's equal to ma sub y. And a sub y, if it's just hanging there, a sub y is going to be 0. But it's different here. Here was when it was moving, and we had m times a sub c. And even though it was moving at a constant velocity, it was still accelerating. Okay? Because the rope or string has to change the direction of the ball or rock as it is. And so here we would have tension minus weight equals 0. And so the tension equals the weight, and the tension comes out to 0.98 newtons. Sorry, it's a little bit messy. Well, it's a lot messy. I'm sorry. I'm still learning how to use this pad, plus my handwriting wasn't very good to begin with. All right, so that's an explanation for those problems, and that gives you a pretty good basis or pretty good example of how to apply the second law to objects that are moving in a circular path.